Welcome everyone to the February 2025 WISE Zoominar. This week we'll be speaking about wave turbulence interaction, and we're excited to have two speakers speaking on this topic and with some quite closely related yet different talks. First, we're going to have Simen Ellingsen from the NTNU in Norway, and then we're going to have Lian Shen and Anqing Huang from the University of Minnesota, with Lian doing most of the talking today. So we're excited to have both of these speakers. I'm going to stop my screen share and I'm going to hand over to Simen to give the first talk. So Simen, if you want to load your screen.
Yep. Can you see my presentation now, Tom?
Yeah, it looks good. Looks perfect. So take it away.
Jolly good. Now, thank you very much, Tom. Thank you very much to the WISE Zoominar organizers for giving me this opportunity. It is very exciting to present now some of our recent work on wave turbulence interactions, parts of various projects. Now, this is roughly what I'm going to talk about. I'll give you some background about the main processes of wave turbulence interactions, or at least some of them. Then I'm going to try something new. going to try to give a kind of cartoon picture about what happens when waves and turbulence meet. This is very breaking news to me, very new in my mind. So this is very much my understanding as of today. And perhaps I'll tell you something else in a year, and maybe someone will shout at me. We'll see. Now, then I'll turn to our experimental setup, because I'm going to talk about experimental work mostly. And some insights from the experiments. I've been presenting experimental work on wave turbulence interaction at WISE for a while, so I'll go very quickly over most of the things that I have talked about several times before, and I'll focus on mostly on the new material. So first up, what do you mean turbulence? That is quite important in this WISE context, because one man's turbulence is another man's slowly varying background current. Because turbulence comes at length scales all the way from millimeters up to 100 kilometers, as we know. So what am I talking about when I say turbulence? Well, a lot of the WISE community will be very familiar with the middle scale here, Langmuir turbulence. I'm going to look at the smaller scales. First of all, I'll look at the waterside turbulence only. So I'll not look at the air above, which is another super interesting question. I'll look at turbulent length scales that are of the order of a wavelength or smaller. Bearing in mind that turbulence is always broad-banded, so you've got a whole range of different scales at once. And I will consider deep water in the sense that the bottom boundary layer, the turbulent boundary layer at the bottom, doesn't have much of an influence. So this is the kind of system you see to the right. These are measurements by postdoc Olav Remke. Turbulence floating by to one direction and the waves propagating upstream on the other, and what happens to the waves and what happens to the turbulence. Why does it matter? I'm not even sure I need to go through this. Fundamentally, in nature, where there are waves, there is nearly always turbulence. And both of them play very important roles in the Earth and natural system, and they change each other quite significantly. So all the WISE people know all this stuff. The waves are key to air-sea interactions, transferring energy, momentum. They contribute to ocean transport of floating matter. They provide challenges at sea because waves can become very big. Turbulence controls the transfer of gas and heat between ocean and atmosphere, and it mixes the surface water into the deep, all the way from millimeter scale to 100 meters. And we know that it mixes the mixed layer, Langmuir turbulence. So we've got three avenues of investigation. We've got field studies, simulation, which Lian is going to talk about, and lab studies. All of them are necessary, I would say, and all of them have their pros and limitations. I'm going to live in the bottom right corner here. So the key processes, I'm going to mention four of them. The first one, which I'll not talk very much about, is that waves that come onto turbulence are scattered in different directions. What I'll do now, I'll do something unusual for a talk. I'll give you lots of conclusions first up, and then I hope to have time to actually back some of them up. So this is something I won't talk much about because I've talked about it before, but the scattering we and others have found is dominated by the largest turbulent structures, and to the extent that theory, which really should not work, because theory using ray tracing and WKB actually gives the right ballpark estimate of the diffusion of waves, which it has no right to work, but it kind of does. Next, we have this linear process, I would say. This is an infrared image of turbulence waves coming from above, periodic stretching and compression of eddies. So this is a linear process. It grabs hold of turbulence, stretches it, and basically leaves it the same way it was. More interesting in this context is the second order nonlinear process, where the Stokes drift grabs hold of eddies, tilting them streamwise and stretching them to intensify vorticity. So this is the key process behind what I'm going to talk about. So naturally, well, what happens is this acts at the kind of smallish scales that I am talking about. What it does is it changes the Reynolds stresses, sometimes quite drastically. And I believe there's reason to believe that it is possibly this process forms the first seeds of Langmuir turbulence. And now's the new bit. Together, for this to happen and to have a steady state process, it is actually necessary that an Eulerian mean current is set up, which partly opposes the Stokes drift. Now, this Eulerian current, which I hurry to say is not our invention in any way, I'll go through that. It doesn't incur any net Eulerian mass flow. Actually, it cannot because due to momentum conservation. And it has, in fact, been both predicted and observed before, but I don't think it's well known to this particular community. I will not talk about dissipation attenuation, which is another super interesting and important topic that I will not discuss. I'll also not discuss. There's been a discussion in the field for a while whether waves can actually create turbulence. I'll leave that to one side. I'll anyway just assume that the turbulence is already there for whatever reason. When waves and turbulence meet, the picture is this. Waves and turbulence each live happily when the other is not present. When the two meet, all of a sudden, they're not happy as they were anymore. McWilliams, Sullivan, and Wang, in their famous paper, use the term spin-up, so I'm going to use that as well. Waves, of course, have a Stokes drift. What occurs is that the Stokes drift, or at least this is my understanding as of now, the Stokes drift grabs hold of the turbulent vertical vorticity, tilts it forwards, intensifies it. And what occurs then is that you get a Reynolds shear stress growing, which, when you look into the Reynolds averaged budget, you get a growing Eulerian mean current, which has roughly this kind of shape. And after a while, a new equilibrium state is reached, a steady state, where this anti-Stokes flow has been set up. Now, it's not really equilibrium, it's pseudo-equilibrium, because clearly the energy is going to dissipate and needs to be replenished. But it's a kind of happy marriage now between waves and turbulence. And some upshots. The higher the turbulence, the faster the spin-up. But in fact, the final current doesn't depend on what the turbulent level is, but on the level of anisotropy between horizontal and vertical Reynolds normal stresses. Now, the question that pops into mine and other people's minds, I suppose, is this paper a few years ago by Monosmith, Cowan, Nepf, Magnodet, and Tai, who analyzed a number of different experiments and found, bafflingly, that there was always a counterflowing Eulerian flow, which seemed to locally cancel the Stokes drift, not just globally like the Eulerian return flow that we know. And they say no existing theory of wave current interaction explains this theory. So a question, could this be it? I just put it out as a question at the moment. You notice it does not exactly cancel the Stokes drift. It sort of almost does, or at least partly does near the surface. In the deep, it actually has the opposite effect. Could it be a solution? I'll leave that question out there. So now for the lab that we're using, I've presented it a number of times before. The water channel at NTNU looks like this. We've got inflow at one end. It runs through a mesh that I'll describe in a moment. And we got waves running upstream, always upstream running waves for a number of really good reasons that I'm not going to go into, but it's also sufficient for all purposes that we've come across. So I should really give credit to my colleague Jason Hurst and his team, because they're the ones who actually built and designed the lab, and I'm very much a guest in this lab. So for the lab itself, these are the guys you need to contact. We've got overlapping projects that look at fairly similar things, so our experiments can actually be combined, which is great. This is some videos of what goes on. These are somewhat old, but they give the idea. At the inlet here, you have the active grid, which are horizontal and vertical bars that spin around, and it allows you to tailor the kind of turbulence that you want. You get waves propagating upstream, and we've got this piano key type of wave maker. At the downstream end, we only look at plane waves here. It's about two meters wide. It says a meter deep, is actually half a meter now. And the test station is 11 meters long. But the waves, because of the treadmill that they go on, actually propagate about 25 meters with the group velocity. And so the turbulence takes about 30, 40 seconds to traverse the test section. So it's got some time to interact with the waves. So this is the experimental team that has been working in what I'm presenting now in different parts. So it's important that the right people get the credit. I normally say that I have an important job during experiments, and that is to be elsewhere. And because I tend to just cause trouble. So Ben, former PhD student and postdoc, Olav, current postdoc, my colleague Jason, who's professor and then postdoc, Priyanka and Amelie, and Ali, PhD student. So first, a little experimental insight into the process that I described, that waves are changing turbulence by tilting and stretching. We did experiments on this, but to review, this is by no means something that we were first to study. We were perhaps last so far. So there's been plenty of theory. I think one of the main papers probably is the Shire and Belcher 2002, a rapid distortion theory paper, very much cited. There's a, a paper by Ardoin Jenkins. There's been a number of numerical investigations. I'm sure Lian Shen will tell you in a moment. He's behind a number of them. And it's been experimentally observed many times, but we looked into it with a different view. Now, here's just the bird's eye view, just to give you a kind of impression of what goes on. What we've done here is we heat the surface of the water coming in with a heat lamp, then film the whole thing with an infrared camera. And now you see, before the waves are just starting to come in, you got turbulent structures filling the whole thing. After a while, you will see that the turbulence begins to bunch up in bigger structures. So there's quite a marked difference. So this is just a demonstration of what goes on. And I think those who are familiar with it will immediately think, well, Langmuir turbulence. It might be a question of what you call things, but it is certainly very closely related. So you see that the waves really do change the turbulence qualitatively. If you plot, just to take a strip or a cross-section right across, you plot that in time, you see the development like this. The turbulence starts out quite small structures, ends up with these big ones. And during the spin-up time, it seems to me, at least to my eyes, although this is perhaps just so you see what you're looking for, but that it's the smaller structures that seem to grow into gradually larger Langmuir type structures. Anyway, a couple of experiments. The first one considered groups of waves. We measured the velocity in the cross plane. The other one we measured in the other plane. This is what it looks like then. Turbulence coming down, waves propagating upstream. So for this first experiment, there were groups of waves. Now we focus on the streamwise vorticity, or the mean square streamwise vorticity. So measurements were performed long before, just before, and just after the passage of a group of waves. And one finds that the mean square streamwise vorticity actually is increased drastically, not just a bit. In all cases, we tried 4 different turbulence types, and as always, 40 to 60% increase. So this is not a small effect, it's a big effect. Then for the Eulerian return flow. Now, I'm calling this from my I'm telling it as my personal story. It's an unexpected journey. In the end, we ended up with involving quite a few people in this paper. We just submitted this paper now, a large paper on this topic. So it started with probably 4.5, 5 years ago that Ben made a discovery in our data, which was surprising to us, because the group of wave comes up and we measure the mean flow, or he measured the mean flow before, but then after the group had passed, the mean flow was different. It had changed in the opposite direction to the waves. It's roughly the same order of magnitude as the Stokes drift, a fair bit smaller, but still not insignificant. So what is it? So what is this? So we tried thinking through the alternatives, discussing with a number of people at the WISE conference in Brest. Well, it's not the Eulerian return flow because it's very concentrated near the surface, and that is not. It's not the viscous surface flow that comes from wave dissipation and waves passing on the momentum, because it's got the wrong sign. And anyway, that's concentrated much closer to the surface. And it's certainly not Coriolis related, because the Coriolis force is negligible in such a small geometry. So we went back and reanalyzed some older experiments, also a couple of other experiments with regular waves, where the waves are just running continuously, and we always find the same thing. The mean current is always different with waves and without waves. And here I plotted the Stokes drift for comparison. You see in this particular case, the flow is always a bit smaller than the Stokes drift, and it also turns around and so it starts pointing the other way again. Now there's this offset between the different curves. We corrected then for the Eulerian return flow that we expect to be there, and that seems to account for it. It's very good. Tried a number of different cases. It doesn't always fit equally well, but for reasons that I think we can explain, because some of these cases are a bit different. But in every case, you get the same kind of trend. Turns out there's nothing new under the sun. This exact phenomenon, or at least I think it's, I think it's the same phenomenon exactly, was described very well in a theory paper by Brodie Pearson, 2018. It's a paper that I think it's fair to say is largely overlooked because it's cited 11 times, even though it really should be highlighted. Is the a bit from the abstract: a near-surface Eulerian current opposes the Stokes drift. It arises from an interaction between Stokes drift and turbulence, and it is antiparallel to the Stokes drift near the surface, changes sign at depth, and integrates to zero over the depth. So that sounds like exactly what we've got. Here's a figure from Pearson's simulations. Now, I dug further into the literature, and it turns out if you go to the sediment transport community, where they look at the scour and the sediment transport in a wavy boundary layer at the bottom in shallower flows, it seems that everybody knows that the waves change the near-surface mean current. The focus, though, is more on the boundary layer, so it's not always highlighted. It's been observed a number of times in this community, and there has been theory and simulations. It's not easy to compare because they tend to focus on shallower bottom boundary layer type flows, but they all seem to rely on wave turbulence interactions at some point. And it's been seen also in simulations. Baru, for example, observed it and merely said it should be studied further. Kawamura also saw it in his LES. He noted that it's stronger for stronger Stokes drift. There is also a similar current in a very interesting recent paper by Fujiwara et al. I'm a bit confused whether it's the same thing, so this is something to look further into, but a very similar kind of Eulerian flow. Again, not a major focus of the paper, but definitely in there. So for the spin up, as mentioned, things begin to set in. So for a theory, you begin with a triple decomposition, trying to split the velocity field into Eulerian mean, wave, and turbulence. Now, following Brodie Pearson, we plugged this into a suitable version of the Craig-Leibovich equation with a number of assumptions and doing a Reynolds average, ignoring some terms for better or worse reasons. We end up with this relation, or actually Pearson does. So on the left-hand side, you see that there is a rate of growth of the Eulerian current. On the right-hand side, you have this Reynolds stress due to the stretching and tilting. So now, a theory, if you can come up with an expression for the right-hand side, that would help you explain things a little. Now, we contacted the real expert on this, Miguel Teixeira, who developed the rapid distortion theory following Teixeira and Belcher 2002. To make a long story short, with some rather coarse approximations on many levels, still it comes up with an approximation for the change in current before and after the wave group. In this case, the system doesn't reach an equilibrium stage. And it's qualitatively and quantitatively reasonable, even though, and I was almost shocked that it's so reasonable. It's but it seems to capture the fundamental physics. For the steady state, we go back to Pearson. Again, you take the two different components of the Craig-Leibovich equation, go through a bit of maths, combine them, do the Reynolds average, ignore a couple of terms, which may or may not be warranted, but you end up with this equation. It's clearly only valid very near the surface because we've ignored a number of terms as being a lot smaller than this, which is the Stokes drift. Anyway, as you can see, this is the Eulerian current on the left and the Stokes drift gradient on the right, or the Eulerian current gradient on the left. Can we test this in the lab? That's a question. Now, first we have to try and tease out these Reynolds stresses from our experiments. That's not so easy. So a big effort went into trying to separate the total velocity field into waves plus turbulence. That's a story for another day. But we end up with this, which is sort of my final result slide. You see here that this first experiment here, the Reynolds stresses are very noisy. The experiment just wasn't designed for this kind of analysis. And this weird phenomenon up here, I'm not sure I can tell you it's definitely true. But as you can see, it really is a decent match. It obviously has consequences for ocean transport. I think Tom can tell you a lot more about this. Bigger objects that penetrate deeper will probably be affected differently. All this is in the air. I'm just throwing it out. Does it have consequences for dissipation? Probably. Another big discussion for another day, but something definitely to look into. And this is my last slide instead of a long list of conclusions. And I'd like to give special thanks to these people on the left who helped out with discussions and equipment and a number of things. So thank you very much indeed.
Thanks very much.
Hopefully,
Thank you. That was very nice. Thank you. Let's see if we have a couple of questions from the audience. If you have any questions, you can unmute and speak, or you can raise your hand, whatever you want to do. See if we have any questions.
Simen?
Hi.
This is Alvise.
Hi, Alvise.
Hi, nice to meet you. Great presentation. So just a quick question. Do you think the consequences for the coupled numerical model where waves and the ocean model interact at some points, for instance, when waves passes Stokes drift to the current, but this aspect is overlooked in the numerical model. Is that correct?
Well, I'm not an expert on the models. So there are others in the audience who are. But it seems to me that if you are to include the Stokes drift in the transport models, then this is the same order of magnitude. So it shouldn't be negligible. But how it goes into models, I'm not the right person to answer.
On the same topic, the turbulence levels in your experiments are maybe higher. Do you expect? Can you say anything quantitative about the extension?
That is true. Our turbulence levels are higher, well, at least than, well, it depends on the weather, right? But they are higher and the waves are a bit smaller. So, according to the theory, the same thing should go. And so these things need to be looked into, yeah. But as for let's say the turbulent Langmuir numbers, we can't get as low as you can go in the ocean. But yeah,
okay.
We cheat a bit.
Thanks. Do we have any other questions from the audience today? Then I think we're going to, it's final chances. We're going to move on to, thanks Simon, thanks a lot. And we're going to move on to the second speaker. Lian, would you like to start your screen share? Yeah, let's go full screen.
Hello, my name is Lian Shen, and I'm from University of Minnesota. And I'm going to present some numerical work and done with Dr. Anqing Shen, and he goes by Elliot, and also Dr. Binqing Dan. Okay. And well, it is such a pleasure to give my talk after Professor Simen Ellingsen. And by the way, we have been collaborating. And today we talked about different aspects of work. And yeah, okay, so his nice seminar actually helped my explanation a lot. Okay, so you can see things are very interesting, consistent. So the title of this presentation is a little bit specific, but probably I should start with the general bigger picture. Okay, so what we are looking at is wave turbulence interaction in the upper ocean. And this is the famous Lemieux circulation phenomenon. Okay, and it got its name, and it's for this audience. Actually, I don't need to introduce this from Lemieux, and then that is due to the bigger counter rotating vortices underneath. And also, this audience is so aware of this and probably much better than me about how important the Lemieux cells are in the upper ocean processes. So let me just move on. And so here's one example about our study using computer simulations. And this one is about Lemieux circulations in shallow water. And then the bigger counter-rotating cells can touch the bottom of the ocean, and it can have consequences. And from a modeling point of view, then one big question is the law of war still there? Okay, is it the same, or is there anything we need to be careful about? And how does that change the shear stress at the ocean bottom? And so in the papers listed on the lower right corner here, and then we did some work on this aspect. And what we found is the log law of the war is still there, but it can only exist when the Reynolds number is large enough. So at the low Reynolds number actually disappeared for a little while. And then when the Reynolds number further increases, that will be realistic Reynolds number. Then it reappeared. But the range is narrower, and in terms of modeling, then we need to be careful about that. And then we look at some fundamental dynamics of wave turbulence interaction. And in this numerical setup, then we generate isotropic homogeneous turbulence in the bulk flow, and then let a monochromatic wave passing it. And this one is periodic boundary condition. So basically that is saying the wave keep passing it. And then we did some analysis about the turbulence in the wave field. And what is essential here is due to the orbital velocity of the wave, then basically it applies a string rate field to affect turbulence eddies. So for those vortex structures, they are being continuously periodically being turned this way and that way, and they are being compressed, stretched, periodically. But the net effect is not zero. And this can be seen from the concept of, let's say, Stokes drift. And we all know in this case, the wave propagates from left to right, and then the orbital velocity at the wave crest to the right is larger than the orbital velocity at the wave trough to the left, and then the net effect is this Stokes drift in terms of momentum transfer. And so these are very well-known concept. And then when it is applied to the Lemieux circulation, then there's this Craig-Liebovich theory, and that was based on a series of very nice papers written by them in the 1970s and in the following years. So a brief introduction about the Craig-Liebovich theory is it started from the velocity and actually it analyzed the vorticity field. And then what is done here is to decompose using Helmholtz decomposition, to decompose the flow velocity into the rotational part that corresponds to the wave and the rotational part that corresponds to vorticity, turbulence, so on and so forth. And then okay, for the vorticity evolution equation, then it contains both the rotational velocity, that is wave orbital velocity, and the velocity associated with the rotation motions. And then decompose the flow field into different time scales and what is called slowing invariant motion and also fast motions. And the slow, faster that correspond to the wave period, wave time scale. And those are slower than the waves are called slowing motion. And the comparable or smaller called fast motion, right? And then using some order of magnitude estimation and perturbation analysis, then the CL theory did something really nice to obtain the Gaussian equation for the slowing motion and also fast fluctuation motion with some high order terms discarded. And then for that, it can be plugged back into the slowing varying motion. And eventually got this Gaussian equation for the vorticity in the slowing time scales. And from there, it goes back to the velocity. And so if we compare this velocity Gaussian equation to the NS equation, then what is shown here is this extra term that represents this wave effect called this vortex forcing term. Okay. And so that basically is the cross product of the velocity vector of the Stokes drift and the vorticity, okay, at this slowing varying time scale. These are their theory mathematically, okay. And to visualize this in the physical space, then what this extra term, this vortex forcing term, can be seen from this cartoon. That is, if we have a mean current and caused by, let's say, wind shear, okay, and okay, if there's a span-wise perturbation, then there's a vertical vorticity generated. Okay. And now, if there's a wave, and due to this Stokes drift, and then okay, these vertical vortices are turned by this Stokes drift from vertical to horizontal direction. And that was considered a major mechanism for the generation of Lamiu circulations. Okay. So these are the classical theory, and then okay, for a lot of simulation works, then they were based on this theory. And this is a very nice theory, has been very successful, okay, yeah. But meanwhile, its limitation is it focuses on the slowing motion, large scale, okay, and motions. And that is what is called a wave phase averaged, okay, yeah. And that was very successful, okay, yeah. But it does not capture all those small scale processes. Okay? And so what we are doing here is a approach that is different, is we try to get one step further. We try to directly resolve the wave phases, okay, to capture time scales, length scales, okay, comparable to the wave or on the wave. And we can see, okay, well, from the talk before me, okay, then, okay, in Simen Ellisen's group, and also I saw from the audience, there are many, many excellent experimentalists, okay. So nowadays, they can measure a lot of things wonderfully, okay. So therefore, a lot of details can be captured, okay. So the question is, how important are they? And from the talk just now, we can see they are important, okay. So that is what we do numerically. We want to resolve the wave and the turbulence directly without the approximation of CL theory, okay? Without using Stokes drift. We let this kind of velocity, mean velocity, those currents, let them be captured in the simulation directly. Let the wave be captured directly without using this US. Okay, so what is done here is in the simulation, then we use a very complex deformed grid, which changes at every time step to evolve together with the wave, so that we can capture those kind of processes. And the numerical details, I will skip that, and they can be found in the papers listed on the lower right of the slides. Okay. So as a test, then we simulate the interaction of turbulence with monochromatic wave train. Okay. So what it does is, well, okay, we capture the vortices underneath the wave directly. And in this case, this is the visualization. Then we put particles on the wave surface and to mimic those floating materials at the water surface to see those kind of wind zones and at the water surface. And we can see they are captured. Okay. Or another way to see that is, let me show a top view. Okay, top view. Okay, this water surface looking from above, and those particles are randomly put on the wave surface, and then let our simulation starts, and the waves are propagating from left to right. Then we can see those kind of floating particles merge into those kind of long streaks, okay, to show the formulation processes of laminar circulation. Okay. So those are the work done previously. And then, okay, well, okay, also, okay, this is the physical picture very consistent with what Simen just showed about the vortex dynamics. Okay, then we can use our simulation data, which is in 3D at a different time consequence, to look at these vortex dynamics, how they are affected by the wave field. Okay, then we can see actually look at the Lagrangian averaging of vorticity equations. We can see it has different terms. And this blue curve shows the physical process of the vertical vortex being turned clockwise by this mean effect. This is as expected. And what is interesting and important is at the time scales parallel, comparable to the wave, okay, or underneath the wave, okay, shorter than the wave period. Then we can see those vorticity and velocity stream rate, they are correlated in a sense, just like Reynolds stress. Okay, and so therefore, okay, the net effect is they oscillate, but they are meanwhile they are turning clockwise at the same time. Okay, so these two processes work together to generate the vorticities in the laminar cells. And by the way, this vortex dynamics was captured very nicely by the CL theory. Okay, yeah. So therefore, okay, this result can be viewed as direct numerical evidence to support the CL theory. Okay, and so that was some of our work a few years ago. And so linear process about the vortex dynamics is captured very well by the CL theory. But the question is, what else? Okay, how about some high order statisticity, like nonlinear terms, like Reynolds stress, like turbulent kinetic energy? Okay. And here, okay, from our numerical results about the Reynolds shear stress, then we can see they are highly correlated with the wave phase. In this case, it is higher magnitude under the wave crest and low magnitude on the wave trough. Okay. Same variation can be found for Reynolds stress or different components of Reynolds normal stress and TKE. Okay. So I will skip the details, and here I just want to show some final results of our study about that. So this figure shows the pre-multiplied spectrum of velocity fluctuations, so in streamwise direction. So that is a part of the TKE. Horizontal axis is the frequency. So basically that shows the frequency spectrum. Okay. At the low frequencies, that is what people usually look at. At the slow time scales, according to CL theory, and those are the things people are familiar with. But what is interesting here is at the frequency that is comparable with and even high frequencies, those are the small scales in time and space. And then we see they have another peak, another peak, another peak. Okay, and those effects actually turns out to are important. And on the table on the right, then what we showed here is about the TKE energy production. Then for the large scale, slow scale, they account for about 60% of the energy production to TKE. But meanwhile, for those kind of sub-wave scales, then they contribute about 40%. Okay, and those are the things missed in the past. Okay, and what is interesting is for the traditional modeling in the community, then they can capture those 60% very nicely. Those are very good model. But the thing is, there are other 40% that was missed before. And so our study showed they are important. So with that, okay, let's move on to things more complicated. And that is some work we just published a couple of months ago. And that's in a paper by Elliot and Bingqing and myself, okay, a few months ago. And so what we are looking at is some cases more complicated. In the real ocean, okay, then the waves are complex. They are never some monochromatic wave infinity and just keep repeating themselves. Okay, and here is one illustration from our simulation, and it's already simplified a lot. So the question is, if we wanted to capture that in our simulation using our boundary fitted grid, which evolves at every time step, then the computational cost will be very high. Okay, probably that is something we cannot afford. So the question is, can we reduce the computational cost? But meanwhile, we really don't want to sacrifice this wave phase resolved feature because we just showed they are important. Okay, so what we did is we designed some numerical scheme which we liked very much. Okay, so let me explain how we did that. First, we did a Helmholtz decomposition to decompose the flow velocity field into a rotational wave and a rotational turbulence. Then, okay, well, for the velocity field, then we decompose that into wave and the rotational part. Wave, then we know it can be solved by even potential flow or Eulerian flow, okay? And then, okay, the thing is, for the rotational part, if we put this decomposition into a Gaussian equation, then we know, okay, well, okay, for nonlinear terms, there are cross terms. Okay, so that is where Reynolds stress comes from. That is where all of the interesting thing in fluid mechanics comes from. Okay, so after this decomposition, then we can see there are interaction terms in this Gaussian equation for the rotational flow part, and they interact with the waves. So basically, we can let this wave effect to influence this Gaussian equation, those terms directly. Okay, so therefore, okay, this is without the approximation of Stokes strip. We let this influence directly. But here, okay, we still have this boundary fitted grid code, scheme. Okay, so we want to do one step further. Okay, otherwise, okay, if we still keep this wave shape, then free surface boundary conditions will be very complex. Okay, so let's not go to their details. Basically, KBC and dynamic boundary conditions, they are complex. That is what we have been doing. So what we did recently is we used Taylor series expansion to expand those boundary conditions from the mean water surface. And then, okay, we assigned different roles to the wave part and to the dynamic surface part, to the rotational part. Okay, so basically we let the wave to be in charge of the surface elevation evolution, and for the surface normal direction of dynamic boundary condition, let the wave part to be responsible for that. For shear stress, then we let this physics part to be responsible for that, okay, which is reasonable, okay, yeah. And then, okay, with that, we move on to study, okay, the effect of a wave group on the turbulence underneath it, okay. So this figure is from literature from Smith's JPO paper. That is a field measurement near Hawaii, okay? And so what is shown here is vertical axis is the distance in space, horizontal axis is time, and these field measurements shows the wave group of waves propagating in the ocean all the time, okay? So here we can see, for example, here's one group of waves, then in different times and in space, they propagate, okay? And we know the wave group propagates at the group velocity, okay? And for the wave crest, the wave trough, they propagate at the wave phase velocity. And they are different. And in deeper waters, they differ by twice exactly, okay? So what we did in our recent work is we look at the problem of a packet of waves. So basically a wave group, okay, to let it propagates in this flow field to interact with the turbulence underneath it. Okay. So here, the wave packet in our numerical model, we have a number of waves, not a lot, okay, 5 of them, okay, and they have an envelope and to prescribe the spatial variations, and let it propagates that. And what is interesting is for this simulation, we did not use this boundary fitted grid we used before. We used our new numerical scheme, which I just introduced. Actually, it's on rectangular grid, but meanwhile, it keeps the feature of this wave phase resolving to simulate this. Okay. Then let's see what happens. Okay. So here, okay, is our numerical simulation results. Top, it shows a sketch of this wave group, which propagates from left to right. And this middle contour is a top view at a plane, okay, that is slightly below the water surface. So this top view. And what is shown here is the vertical velocity fluctuations. Okay? And the red means positive velocity, blue means negative velocity going down. Okay, so we can see when the wave group passes it, then the turbulence intensity got enhanced. Okay, and then this bottom one shows the span-wise averaged velocity fluctuation magnitude. So again, we can see when the wave group passes, then the turbulence got enhanced, right? Very rapidly, okay, very coherently with that. Then after the wave group passes, then they die down, okay? Okay, so this shows the effect of wave packet on the turbulence. And with that, we can do some analysis, and due to time consideration, I will just show some representative results. So what is shown here is we do triple decomposition and to look at the statistics that is done with respect to individual waves, as shown here for this vertical cross-section, or we can look at a larger scale to see what is the variation with respect to this wave group. So here for the figure on the right, bottom right, then the wave group and waves, they propagate from left to right. And so what is shown on the right is before the wave passes, and then what is shown on the left is behind the wave group. So after the wave passes, and things got enhanced, and this is the vertical cross-section. So I'm going to show a few statistics about the vertical cross-section. This, for example, is about the effect of a wave group on the vorticity components. X is streamwise vorticity, Y is span-wise, and Z is vertical vorticity. And we can see after the wave group passes, then behind it, the streamwise vortices got enhanced. That is persistent, long-lasting effects. And that is just like Lamian circulations. Okay, so actually that is the process, illustrate that processes. So therefore, that shows that process. Similarly, for velocity fluctuation components, then U, the left figure is span-wise velocity, and V is this is streamwise, I'm sorry, okay, left figure is streamwise, middle figure is span-wise, right figure is vertical velocity fluctuations. And similarly, due to Lamian cells, then the velocity fluctuations in the span-wise and in the vertical directions got enhanced, but not the streamwise velocity fluctuations. Again, things are consistent, okay? And we further found that actually this kind of enhancement effect can be scaled by the wave group. Okay, so here we tested numerically the different wave steepness, and of course their effects are quite different. But after the scaling, then we found actually the enhancement effects can be reconciled into some magnitude that is collapsed. Okay. And the last result is we can further using the numerical data to look at this turbulence enhanced effect at different time scale or length scales. So here is a vertical cross-section, and horizontal axis is the length scale. So on the left is a small scale, and they are enhanced near the water surface. And to the right, that is larger scales, then they are enhanced at some intermediate depth below. Okay. So that means when a wave group passes, then turbulence underneath it at different length scales, they are responding in different ways for that. So with this, okay, this is my summary page. Okay. And so what we did is we showed some mechanism study about Lamian circulation and Lamian turbulence, and we showed well, CL theory is very successful about the large scales, but for small scales, then there are certainly something missed, and that is not surprising because CL theory was designed to have a low-pass filter and to capture those large scales. And nowadays, with the improvement in numerical scheme and the improvement in measurement techniques, then okay, people are able to capture small scales. So therefore, okay, now okay, we really start to realize how important those small scale processes are. Okay. And then okay, in the most recent paper listed here on top of the references, then we design a numerical scheme that can now okay, be more applicable to more realistic setting in the laboratory and in the field. Okay, and we are quite excited about that. And we very much look forward to collaborating with experimental colleagues to look at those effects. And there are some other the processes I mentioned, and for references, they can be found in the papers listed here. With that, I better stop here. Okay, thank you.
Thank you very much. Thank you. That was very nice. Very much, very impressive by the high quality of the numerical simulations and what we can do nowadays. Thank you. Let's see if we have any questions from the audience to our speaker.
Yes, I have one question. Hi, great talk. Thank you very much. Something related, imagine that you have a Stokes wave, and the boundary layer, the classical boundary layer beneath it. Is this as a hydrodynamic problem? Is this flow, is the boundary layer beneath a Stokes wave? Do you think is linearly stable or unstable? Because there have been arguments, Babanin and other
yeah.
They argue that non-breaking waves can inject turbulence into the ocean, and so I thought, okay, if that is the case, it means that there must be some instability, hydrodynamic instability of the boundary layer beneath a Stokes wave. So, and I'm curious to know what you think about that. So, is the flow unstable? Is linearly unstable below the Stokes wave?
Thanks.
Yeah.
That's Lian's answer. Yeah.
Yeah, well, excellent question. And so for that one, like in our the paper written by Elliot, okay, in the 19 and 20, we touched this subject to a certain degree. And what we found is if this is just a purely Stokes wave without any turbulence, then we didn't, from our simulation, we didn't observe this instability. Okay, by the
No instability. Okay, that is in agreement with I did hydrodynamic stability analysis, and it agrees with my results. I also didn't find any instability. That's great.
Okay. Yeah. Okay. And meanwhile, okay, if there are turbulence in the flow field, if there is already turbulence due to shear or due to some other processes, then there is a pathway for the energy to go from the wave to the turbulence. Okay. But so our experience, the turbulence has to be generated somehow. Okay. And then there's an energy path, and then the turbulence will be amplified.
But has to be finite amplitude turbulence, right?
Yes, exactly.
No, because I make the analogy with in-channel flows. If you think about pipe flows, they are all linearly stable. And the instability only occur when you basically put a finite perturbation that will lead to all the self-sustaining processes of Wall-F and so on. So is this the same for the boundary layer beneath a Stokes wave? That a finite perturbation will trigger...
Yeah, based on our simulation, we did not find that, at least for the Reynolds number we can touch with the numerical simulations, we did not find such instability mechanism just for the Stokes wave.
Yeah.
I mean, even with the viscous, like even if we consider the viscous layer at the wave surface, but we did not observe the instability mechanism.
Yeah. Well, yes. Yeah, this is largely consistent with what you just
move on. So we have another question from Seth Zippel. If you would like to unmute and speak.
Hi, really nice talk. I'm really interested in this stuff. I published a paper last year in 24 with Malcolm Scully about interacting groups and turbulence. And one of the things that we were seeing was that the pressure from the wave group seemed to interact with the vertical velocity from the turbulence that resulted in a net pressure vertical velocity correlation.
Okay.
And I was really interested to see if you see something similar in your simulations. This is something was sort of hard to tease out of our field data, but we were really interested if it's something that could be simulated, and we know how hard it is to do free surface flows with turbulence. So I'm really excited to see that you're able to do these types of simulations, and if you see similar things to what we've measured in the field.
Well, yeah, thank you, Seth. And yeah, indeed, from numerical simulations, one advantage of that is it can obtain pressure because we solve for the pressure at every point, grid point, like, and then we can got the correlation terms and to quantify the pressure transport terms and pressure string correlation terms in the TKE budget equation. So that is certainly something we are very interested in investigating, and I very much look forward for opportunity to collaborate.
Yeah, and also like I mean, although we in both these studies, the waves are kind of fixed, like for the first part, the monochromatic wave trend, and for the second part, the wave group that is prescribed. But when we do a full simulation, when we for the monochromatic wave trend, I did find that the pressure work is important. That there is a small deviation that is caused by the underlying the large scale laminar circulations. That it has a distortion effect on the wave, so it kind of creates a small wave group, like a distortion, and that has a strong pressure effect. So I think, yeah, this is a very interesting topic to investigate. Yeah.
Thanks. Let's see if we have any final questions to either one of the three authors present. If we have no final questions, I'm going to thank all the speakers today for their really nice contributions, and I'm going to invite everyone back in about a month from now. Invites will be sent shortly for the next Zoominar. And for those of you attending the actual WISE meeting in Seattle, we expect to release the program in, I think, the next week or two. So thanks very much, Simen. Thanks, Lian. Thanks, Lian Shen. Thank you.